Evening, mother lovers. So, stats paper from 2025. Let's get going. What have we got then? Bag A has 5 red, 4 yellow, 3 green. Bag B has only got red and yellows. What we're doing? We're taking one from A and then another one from B. We're told here they're getting 2 yellows, so both beads being yellow, 3/16. We're going to find probably of getting a yellow from bag B. So, what can we know then? If we get a yellow followed by another yellow, the end of that branch should be 3/16. We can look at top. We've got bag A information. So 4 out of the 12 in total, sorry, 1/3 of them, are going to be yellow originally. So let's just say that we had Y. Let's probably on this one. How do we get down this branch? Well, we timed together to get there. So the third times by the Y should be 3/16. Timed and across by 3 then on both sides. It's not very good. Y. Try again. Will give us 9 on 16. So that's going to go in that little gap there. Lovely jubbly. Looks good to me. We'll do that bit. Nice. Part 2 of this then is to fill in the rest of the tree. Well, there's only 2 outcomes for bag B. So if we've got 9/16 there, we must have 7/16 on the other one. That will repeat itself then on every single branch, because A and B, like selecting from A, selecting from B, those 2 events were independent. So that means that they don't affect each other. So which one we chose in the first bag didn't change these probabilities from the second bag. Lovely. What are these ones then? Well, it's actually going to be easier. We're probably going to have to time this together, I'm guessing, later on. Yeah, we'll be doing stuff with that. So let's make sure all of our probabilities in every row are written with the same denominator. There's actually 12 in this bag, and there are 4 of them were yellow. For the red, 5 out of 12, and the green is going to be 3 out of 12. The reason we do that is so now, if we do 12 times 16, we get 192. That's going to be the denominator of every single one over here. So over 192 for all of these. The value that we've got there, that 3 on 16, let's rewrite that as well as something over 192. What I'll actually do is swap the sides here so everything's matched up. Lovely jubbly. 192 on the bottom then. So that's times by 12 on the bottom. Yeah, it's times by 12 on the top. 36. And now then, to work out the probabilities, we just times the top rows. So 5 times 7, 35. 5 and 9 is 45, yeah. I've got 4 and a 7, 28. 3 and a 7, 21. And a 3 and a 9 along the bottom there, 27. We can double check that we're correct by adding these all together. 35 plus 45 plus the 28 plus the 36 plus the 21 plus the 27. 192. 192 on the bottom. So that means all of these together sum to 1, which is a good sign and it's correct. If you got that by chance, unlucky. Very unlucky you've got that by chance. Looking at this then, very easy for us to do all these bits of information down here. So exact probability, at least 2 are yellow. So let's look at the branches we're going to get. Anywhere we see a yellow, that branch is successful. So yellow, yellow, yellow on the end. This yellow in bag A leads, therefore, to success as well in every way. So this is also success. So for B, we want to add up all of the branches that contain, well, have those blue circles in the end, yeah? So it's going to be 1 over 192, just to draw this a bit easier. And then what numbers are inside those? 28 plus, 45 for the first one, 28 for the second one. And then a 36, 27 on the end as well. Let's add all those numbers together. What do we get? 45, 28, 36, and 27. 136 on that 192 still. Why this is good as well, it's representing the number of outcomes. 192 is the different possibilities. Do you mean the different arrangement you can get from taking one bag from A and one bag from B? There might be that some of them are actually the same. Do you mean that they're the same arrangements? Depending, like, you take, there's 5 different red beads, do you mean, in bag A? So there's 5 different ones just for like which red one you pick. So some will look the same, but it's like you've actually picked a different bead. Do you mean? So 192 different possibilities if you had different beads for all different colours. 136 of them are going to have at least one of them being yellow. All make sense, yeah? Lovely. So event X is that at least one of the beads is yellow, so that's what we've just found here. Event W, is that a green bead is selected. Where do we have some greens? Let's do a green circle and everything. Anywhere we get a green bead. So there's green. Okay. Well, that's fun, wasn't it? So we have that one and this one down here. If we again lead into the successes of greens, we want to find a probability that we get a green. I'm going to write underneath that's green, given X, which is yellow. Okay. So probability when we have conditions, we have that formula. What are we going to get? It's the intersection of the two. So W and X, so yellow and green, over the one that must be true, the X. Yellow and green, there's only one possibility in it. I need to go to green and I need to go to yellow. So I've got that 27 on 192. 27 on 192. Divide that by what we have for X, which is just having a single green one in there. You could go and work these out, add these two together, but it's just the same as this branch, isn't it? It should do. Well, it should be exactly the same because these add up to 1. What we're doing to get this stuff is this times this, then this times this. So we could just factorize out, doing cut out the middleman, add these up, and then times by this. Well, these add up to 1, so we do just get this one. Cancel it down, it's 1/4. So we want to figure out what's this going to give us. So 27 on 192. It's like divided by a quarter in it, so it's going to be the same as times and by 4. So it's a 9/16. That looks good. That's a number we've had quite often today, isn't it? So that's, yeah, always a good sign. Lovely. Looks good to me. Next one. What do we have? Runners. What they're doing? Running, probably. He's got 120. That's a lot of them, isn't it? Oh, bloody hell. 40-meter race. Blah, 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 blah. So we have some values for this stuff. What we're doing? Probably mean deviation. Yep. What a surprise. So the mean. How do we do that? X bar. Add them all up. Divide by how many there are. Added them all up. Gave us 6, 6, 1, 2. How many were there? Bloody loads, weren't there? Yeah, 120. So let's do that. What number do we get? 6612 divided by 120 is 55.1. They're moving, mind. They are moving. Give them that. Standard deviation. So sigma is going to be, we want to add up all the squares, divide by how many there are, and then square the mean, take it away. That gives us variance. So we square root that thing, and that is the standard deviation. Let's fill in all of our numbers then. It's going to be that big one, isn't it? Oh, look at that. 6. No. Nope. 3, 6, 4, 902. Over how many were? Bloody loads, weren't there? And then we take away the number we just found. 55.1. Give it a square. Whack a square root around the whole thing. Let's fill that bad boy in. 364,902 divided by 120. Take away 55.1 squared. Gives me a big old number, doesn't it? Oh, actually quite small, 4.84. Let's square root that afterwards. It seems small already. It's a very small standard deviation. 2.2. The answer being so nice is a good sign, isn't it? 2.2. Lovely. Looks good. Let's circle the other one as well. Beautiful. Let's keep going. The mean and standard deviation for the best times of the 100 runners trained for the 400 meters by Coach B are 55.1, the same, and 3.6 seconds, so more spread out. A 400-meter race consists of equal numbers of the fastest runners trained by Coach A and B. State, given a reason, which coach is more likely to train the winner. Okay, so this is about the spread, yeah? They have the same standard deviation. No, same mean. So when we go to draw them, one of them is going to have that sort of spread. I'll actually draw a bigger line underneath. Oh, come back. We'll get rid of that one. Put a bigger one there. This is obviously time, yeah? Time on that axis. And we have this another distribution with the same mean, whether it's going to be mu or x bar. Well, it should be t bar, shouldn't it? So t bar. The same mean, but different standard deviation. So that means we have less of a spread for one of them. Like one's going to be like shorter, or thinner and taller. So if we think about the best runners, who's the best runners? The people at the very end, yeah? Either way. running will be faster, so less time. Which one goes further is the red one, the one with the highest standard deviation. So what we can think about is the fact that we want the high standard deviation. Who had that? Was Coach B, won at 3.6. So yeah, more reds. That means we want a higher standard deviation, which implies Coach B. Lovely, jubbly. Let's keep going. In the exam, I'd phrase that differently. This is just me explaining it to you. I'd write full sentences like, what are you explaining? Do you know what I mean? Put it in words for them. But the general premise is that, isn't it? Like, there's people over here that's faster. There's more of them than the blues. So because of that, we pick the red ones. Lovely. Number 3, what have we got? On average, 1.5% are defective. So that's going to be a probability, surely. And random sample of 36. Okay, so what have we got? Let's say that X is distributed binomially, yeah? We had a sample size, 36. We had a probability, 1.5, so 0.015. Exactly 2 being defective. So the probability that X is equal to 2. Got our calculator on the left here. Let's whack in some values. With my, is it small still? Yep, still small. Okay, right. Probability of success, 0.015. Number of trials, 36. Number of successes is going to be 2. Calculate. We want the exact one, don't we here? Yes, we do. Top row then. 0.08479. Lovely. More than 3. Okay. So X is greater than 3. Let's do that on here then. So 3. Calculate. X is bigger than 3. That is going to be that 4th value, yeah? So that's going to be 0.00203. That seems very small, doesn't it? But that's not actually too bad. Like, let's just work out the rough expected value we should have. So 36 times that small probability, 0.015, gives me a value of 0.54. So yeah, NP is 0.54. So that's the mean. That's the mean of this thing. Should be that anyway. It's expected mean. So thinking in that way, getting bigger than 3 when you're expecting 0.51 isn't too bad, really. Do you know what I mean? It's a very small percentage, like 1 in 500, that is, get made this big, which is okay, or like have that high of a percentage. Or there's that chance. Do you know what I mean? There's a very small 1 in. If you did this 200 times, you'd expect to have 3 components or more than 3 components be defective once. Lovely. Let's keep going. Once every 6 months, the manufacturer tests whether the proportion of defective components has changed. Okay, hypothesis test, yeah. Random sample of 260 is taken, and 8 are found to be defective. So, using a 5% level significance, complete the test. It's a very big sample size. 8 are found to be defective. Yeah, it's a very big sample size. I wonder if we need to do like a continuity correction. Let's have a new distribution. Y, that's going to be distributed binomially. 260. And P is going to be still 0.015. Doing that then, what do we want to find? Well, we're told an observation, weren't we? 8 are found to be defective. Let's have a look at the mean. So the mean of this, that the expected value, we shouldn't really say mean, it is the expected value. It's just that n times p, yeah? N times p. The 260 times the 0.015 we have in there. 260 times 0.015 gives me 3.9. So the 8 that we have is bigger than the mean. If we draw it out, we have our distribution here. Might not be symmetrical, but it doesn't matter too much here. Our expected value, our middle, 3.9. But what we have, bang over there on it, yeah? On the right-hand side. So when we're trying to find the probability that we have 8 or something more extreme, we need to be looking bigger than 8. So we want the probability that y is greater than or equal to 8. So let's do that. Number of trials is going to be 260. Probability is the same. Successes now is 8. What do we get? We want to have bigger than or equal to 8. That's the 5th of those ones, yeah, just the one above the mean. So 0.044412. What we're going to do with this is compare it to our significance level. So that tells us, I call it alpha, don't know why. It's going to be 0.05. And that then, yeah, we compare to this number. So we have 0.04 on the left, 0.05 on the right. Which one's bigger? 5 is bigger than 4, isn't it? So what this means, the observation that we had, there's a 4.4% chance of that just randomly happening. Our threshold for randomness was 5%. We're saying like, okay, anything that happens, well, it's got more than a 5% chance of happening with that. Okay, that's acceptable. That's normal. Less than likely, or less than that percentage, we're saying no, too unlikely. So what we really have, this 8 that we've seen over here, there is some zone. If I kind of draw another line there, we don't know what number this is. This is some random number that we're going to call the critical value. Actually, that's the name of it, isn't it? The crit value. And that basically means that this little zone is then 5% of the entire probability, with this side being the other 95. And our 8 sits firmly in this zone. And that's the zone that we're saying, okay, no, we've seen too many defective components for our liking to think that we're still only getting this percentage of them to be, or this proportion of them to be defective. We now think that there's something wrong with it. He's tested either direction, actually, so we've done this slightly wrong. We need to redo it. So we need to redo it. Why do we redo it? Two-tailed, isn't it? So really, this is going to change to 2.5. Everything I did there is correct if it was, if we even have one little change. If this said greater than that, he thought there's a higher chance. If he thought his machines were doing worse, do you mean? All that changes now, though, is going to be that this number should be 2.5. And we actually have the same thing on the other side. So bop, 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 bop. That's 2.5%. And when we compared it then, this should have been split up into not 0.05, but 0.025. And that therefore changes the comparison, doesn't it? This is more likely than our actual threshold. Because our threshold got split in two, we're saying there's 5% chance of things that are going to change our mind, but that's 2%, 2.5% on the left, 2.5% on the right. So the 8 we saw actually is okay. It's not past our threshold of like weirdness. It was acceptable. So what does that mean for us? Let's just write down a little note for you to think about in the future. The observation was more likely than our kind of like threshold for weirdness. That's the way I think about it. How weird are you allowing it? I'm allowed to be 2.5% weirdness. As in, like, the smaller you get, the weirder it is. Like, that's how unlikely it's going to be. Only 2.5% times this thing would happen. But what we saw, 4.4%. That's more likely. So, that tells us that we accept H0. Yeah? We haven't seen anything too strange. So, H0 is fine. We've got no reason to doubt ourselves. If this is the other way around, we reject H0. We always commenting on the original thought. That's what we're trying to do. It's basically, this is the first investigation. Like, is it worth us even looking to find out whether we're wrong or not? Now, if we think something's wrong, okay, we'll do this little test first just to see, okay, is our thinking actually valid from the data, or are we just imagining things? If we come back and we reject H0, then we'd go and have a further investigation on H1. But right now, H1 is just kind of a guide for us to be like, okay, how is this bit working? So this bit not equal to tells us it's two-tailed. All making sense, yeah? Lovely. Let's keep going. Number 4. She's doing large data steps. She's doing large data set stuff. Starts with 5th of May. Selects every 10th day after. Name of the sampling technique is systematic in the system. And then the mandramatic at the end. Kate wants to find the regression line of Y on X. What's Y? Rainfall. What's X? Sunshine. Using the knowledge of the large data set, explain how K might need to clean these data. I don't know too much about the large data set, but doesn't that have trace in it? So it's like remove trace. I think it's just TR in it, but yeah, remove trace in Y. It's called cleaning the data in it. Yeah, that's what they've said. Yeah, cleaning the data. So the reason why trace is obviously qualitative. it's a word. We really want to have, when we're going to be doing this sort of stuff, and that we want to have numbers to deal with, not words. So it basically just means remove the words, take your words out. Yep, lovely. Use the knowledge. I've got no knowledge, but I can do something else. State the units. Okay, units. Well, rainfall is millimeters, isn't it? And we want the gradient, so it is going to be y over x. So it's going to be the y ones, millimeters. Sunshine, is it hours? It might not be hours. Whatever units this is, if I'm wrong here, Jimmy, I don't know the large data set stuff. Let's just double check. What's the large data set units? Large data set. Edexcel. Sunshine units. What do we get? We get all large data set. That's what we get. Hours, yeah, obviously hours. So it's going to be millimeters per hour, yeah. Gradient stuff, it's just y over x, dy dx, dy dx. Lovely. Circle these actually. Systematic retracing y millimeters per hour. Next one, interpretation of the y-intercept. So that's this one. What that's really saying, well, y is rainfall, x sunshine. The y-intercept, that really means that if x is 0, what's y? So this happens when x is 0. So when if we had no sun, if the sun never rose, what would happen? Well, it would still rain, wouldn't it? Yeah. If the sun rose, it would still bloody rain, wouldn't it? 0.741 millimeters of rain with no sun. Disaster. Yeah, not what we want to see, but yeah, I think that's what it means. Because yeah, if x is 0, then y is going to equal that. So when we have x is 0, no sunshine, we get this much rain. Lovely, jubbly. What's happening next then? Case teacher is claiming, well, she's claimed already, that the greater the amount of sunshine in a day, the lower the amount of rainfall. That's not what we've seen, is it? No, we've seen a positive correlation. Okay, state given reason, whether she's true or not. No, no, you're lying. Oh, you're chatting out your ass, aren't you? You don't know what's going on. So, what's our reason? Yeah, we've got positive gradient. Positive gradient. That's going to imply a positive correlation. Lovely, looks good. The teacher used all the data for these variables from the large data set from Leeming in 2015 as a sample. We've got the PMCC, negative 0.160. In a suitable test, blah, 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 p-value 0.015. Using 5%, state the hypotheses and conclusion for this test. So, hypotheses, let's get a null. Let's get an alternate. What they're actually trying to do, teachers claim, that's what our hypotheses are always about. Teachers claimed that the greater amount of sunshine in a day, the lower amount of rain there should be. So she's making a claim about the correlation, isn't she? That it's going to be positive. Our hypothesis is always that there's no correlation. Looks good to me. And conclusion then, what's going to happen? Are we going to reject H0? Well, we have, what do we have? Let's circle our numbers to make it a bit clearer. This value and this value. We get, and the 5%. This number has been used to calculate this number alongside the sample. So this number and the sample size has been used to calculate this number. So what this represents is the random chance again, 1.5% chance of any two bits of data, any two random variables having a correlation of 0.160, whether it's positive or negative, doesn't matter. But there's less, 1.5% chance of it being that just randomly. Our threshold for randomness was 5% again. So it's the same thing, yeah? It's the same things happening. Same things happening, but now we've got one-tailed because she has stressed it's positive. Let's actually draw it out here again. Yeah, one-tailed because it's positive. This is representing our correlation. Something like this, always centered on 0 for correlation. We're looking to the right, looking positive, and we're told that we have 5% significance level. So we can draw some line there. This is going to be 5%. This again, this is our critical value. Crit value. And what we're told is that our thing had 1.5% chance. So we are, when we go over it, we're well in this zone, yeah? We're sitting here somewhere. That's us. Does it say anything about the number? That's negative. Well, it's going to be on the other direction, 1.60. Am I being silly about this one? I am, aren't I? Yeah, sorry, lower. So you say negative correlation, you. So I need to draw my graph the other way around. Let's just, well, what we can do. Sneaky. Oh, move you over, move you over. Steal you. Rub you out. Bop, 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 bop. And then put you on this side. Sounds good. Maybe that arrow needs to be a bit better. And then that can go there like that. And you can move over to there. Looks good, doesn't it? Yep, looks good to me. So what were we doing? Yeah, which again, same thing happens just the other way around. This is negative, isn't it? It's negative. Let's fill that in. Lovely. We got though 1.5% chance. That's what we're being told there. So our green line, if you have like a little green zone at this end as well, the green zone is much smaller. That's only 1.5%. So what we've observed, very unlikely. Our threshold for weirdness is quite high. We're even weirder than our threshold. So again, we're going to reject H0 and have a further investigation into the teacher's claim, which does make sense. I don't think K's got. I think K's mad. Do you mean more rain, more sun? No, not at the same time. One or the other, isn't it? Really, kind of by definition. Like what you need for this, you need the opposite for it. Like it stops this. So it should be that it goes the other way around. It should be a negative correlation. Yeah. Describe a sample. It was only from the data set, wasn't it? Yeah, Leeming, 2015. Yeah, it's just all the data from Leeming 2015, is it? I don't think she's done anything less than that. Does it claiming about stuff? Use all the data from, yes, use the data from all the data for these variables from the large data set for Leeming in 2015. So that's our sample. Leeming 2015. Again, I would use a full sentence in the exam. Possible population, we could just do like Leeming in the whole century, 21st century. You could do that, do you mean? Even that hasn't happened yet, that could be in the future. Doesn't say anything about the time that's going to happen. If you want to get a little bit more technical, you could rewrite that as like the 2010s. So like 2010 to 2019 inclusive, just to make sure we know we include them all. And yeah, that looks good to me. Population, like, yeah, it means all of them, but it depends on your viewpoint. Like, there's a population of your school, isn't there? There's how many people go to your school. That's not the population of the country or the world. So population is always kind of dependent on the context. So like, what's a sample? What's a population? A survey? No difference really. It's just the size. Are we talking about everyone that we could possibly ask, or are we not? If we are, census. If we're not, sample. Lovely. Number 5 then is the last one. No, it's not. So penultimate one. What have we got? Height of men in a tennis club are normally distributed with a mean of 183. The H distributed normally 183. Deviation 4.9. So that goes in there with a little square. Find the probability that the man's height is more than 186. So H more than 186. What are we going to get? Let's fill in our thing. We need to change our calculator though over to the normal one. Normal distribution up on the top right. Zoom in a bit. Oh, just let it do itself. Change some of these numbers. What do we need now? Move it out the way. The mean 183. Standard deviation 4.9. We want to be more than, so above 186. Above. Calculate. Is that doing? I'm assuming that's changed. Yeah. Okay. What we got? 0.2702. Don't trust that for some reason. And now next one, between 175 and 185. So I can do that. Between. Move you down a bit. Or over there. 175 and 185. Calculate that. What do we get? About 60%. 0.6072. Do those numbers seem sensible? Well, average height is 183, yeah? This is a 6 centimeters off. And yeah, that looks about good. 1/4 of the people are an inch, about an inch in it. So this is 6 foot-ish. This is 6'1"-ish. Quarter of the people are more than 6 foot. 6'1". Yeah, that seems to match up. How many people are between what's this going to be, like 5'9", 5'10", and 6'1", 60%. Yep, these make sense. Looks good. Always be like a little sanity check. The numbers you get out should seem realistic. In stats, the numbers are going to come from something sensible, because that's the whole point of stats as well. It's like, does this make sense? Like, no. Okay, what have we done wrong? Or like, why is that happening? Investigate further. Right, let's keep going. We got women now. They're playing tennis too. We got a mean of mu, deviation of sigma. 40% are shorter than 170, and 15% are taller than 175. Ooh, find these bits. Okay, so let's have height of women. So height of women. This can go up here now. Then it'll be height of man everywhere. Height of man. Height of man. We'll make the woman look more like a woman. Well, it's not a woman, is it? It's a W. But still, there we go. We don't want that. We want it to be distributed normally with a mean of mu and a standard deviation of sigma. Well, yeah, variance of sigma squared. So what information are we given? Probability that we are shorter than 170. So the height of women being less than 170 is 40%, so 0.4. And we're also told that the height of the women being taller than 175, that is 15%, 0.15. I wrote that as 40. So let's visualize this, make it a bit easier for us. We have the height of women along there. We're going to have our distribution normal again, so doing something like that. Make it a bit bigger, easier to see. Looks good. And we're going to have some numbers. So bigger than 175, let's put that like here, 15%. So that is that 15% in there. And the smaller 170 is 40%. So about there maybe. So that's going to be 40%. That number was 170. This was 175. And now then, we just want to find out where is our mean going to be and how big is our standard deviation. This works in not too bad of a way. It is simultaneous equations in disguise. We're going to use the standard normal. So just some notation, if you're not sure how this works, we have that the standard normal is always written with a Z. Well, like it's just usually written with a Z. I don't think it has to be. Written with a Z. And it's going to be distributed normally with a mean of 0, standard deviation of 1, and variance of 1. That's why it's called the standard normal. Standard in math just means like you've scaled it down to a size of 1, generally, either that or unit, but like you can kind of standardize something, Jimmy, or normalize as well as a word for that. But they've already used the word normal for the distribution. It couldn't be like a normal. It is the normal. Is like probably a correct way of saying it, but standard normal is what we use instead. And we have then a little notation of phi. I think this is phi, that's the name of it, of z. And this is going to be little z because that's going to be one output. This is the actual kind of distribution. This is going to be one element of that, one value of that. So phi of little z is just a shorthand of us finding, it's like the CDF basically, our distribution being less than that value. So just to clarify, drawing that out again, will be the same sort of shape distribution. I'll try and do a better curve again. I'm actually going to steal that one. That was a good one. Let's take that. Oh yeah, look, lovely. Color it in though. Blue. Yeah, it looks good. So I don't know where Z is, little z, but what we can do is we can just put it on there and say that that is just that. Do you mean it's just that area? That's what it's representing. This is going to be little z. We have our peak of the distribution is at 0, and this is little z. So just a shorthand like notation we're writing that with. Reason we want to use that, it's just a transformation. This is what this standard normal does. It's a way of representing every single distribution you can have in a format like that. You can just transform between the two. When I say transform, I mean literally like transformations at GCSE, translations and rotations and enlargements, that sort of stuff. This is just a translation and an enlargement. So what we're going to have, the value for z, this is true for big Z and little z. It's basically a coding. Do you mean z? I do without that one. Is x minus mu on sigma. So that's true for little z as well, and little x. So it's just saying like this is kind of the general description of the coding of the entire distributions. This then is for the individual coding for one of the variables inside it. So let's think how to use this then, because we have this to be true. So if we can then like inverse that, we have that z is going to equal to the inverse standard normal of like the probability of being in a random thing. So this is just going to be some probability, yeah? I'm just going to write it a bit neater, and we'll just write it as like p of little z. Yeah, p of little z, which are the things given to us. There, these bits, that's what that represents. Once we have like it's still the same probability, and we can then set this equal to this thing. So just to explain, once we filled all this in, doing that for these actual values, then we're going to go and have a look on our inverse normal calculator. So we have for the inverse normal that's standard, it's going to be 0 and 1. If you have a calculator that can do the other bits, just do the other bits, because you can just put in the values and you'll do that, and it will give you the actual values out in a second. I'll show you once we've done this version. So area we want on the first one, 0.4, and we want to be below that. So when we do this, we get that z value. So we can see, if I get a little line here doing the right hand side, that we have inverse phi of the 0.4 is negative 0.2533. This is a measure in standard deviations away from the mean. So 40% is 10% away from the mean, yeah? 50% mean, 10% away, is actually a quarter of a standard deviation. So we've got that one value. That turns into a equation using this thing. So z is equal to that. Z is going to be this number. That is z. So we can start filling this stuff in. This should equal, let's move over a little bit. Yeah, this thing, the negative 0.2533, will equal x, the 170 inside, minus mu over sigma. So we can times by that sigma and have effectively that 170 minus mu is equal to minus 0.2533 sigma. Yeah, lovely. Similar thing then for the other one. You can see where the kind of numbers end up being. We have 175 in there, minus mu is equal to some amount of sigma. And to do that then, all we need to change is this number becomes 0.15, and we change this to be above. So if you do it below, it's just the negative of it, yeah, symmetrical. So 1.0364 looks good to me. From here then, what do we need to do? Well, simultaneous equations. I've got so many mu's, so many sigmas. Let us subtract them from each other. So if I do that, I'll do bottom take top. Let me actually write these upside down just to make it easy to do that subtraction. So move you down, move you down, move you up. So yeah, now doing top take bottom. Left hand side is 5. Just 5. Just 5. And then this thing, take away a negative, is like adding it. So 1.0364 plus 0.25. I'm assuming there's still 3s, who knows? Who knows my writing? What do we get? I'm going to get a number of 1.2897, lots of sigma. So that means sigma should be 5 divided by that big number. 5 divided by all those decimals, we get, let's write it first. So 5 divided by 1.2897 is going to be 3.877. Yeah, that's good for sigma. Take that value then, plug it back into here, work out what mu is going to be. So if you think about that, add this over, take this away. Mu is 175, take away 1.0364 times by that number we just found, 3.877. 175, take away 1.0364 times by 3.877 is equal to 170.98. Yep. Does that sound good? Well, let's look. Does it fit into what we've talked about, what we've discussed? Yeah, it's in between there. It had to be, didn't it? So we can put it kind of like in that region. Yeah, it's in there, isn't it? 171, pretty much. Imagine it actually is 171, the value they've used. We might have rounded some things along the way, not get exact values out. Do you mean? Stats isn't an exact science. It's a little bit wishy-washy. It's a little bit subjective. A little bit, oh, okay, we'll try this. See what it looks like. What actually works. What's easy to do. Yeah, that looks good to me. Find out. We've got these values. Next bit then. Probably that both players, or we've got a man and a woman. Okay, both of them between 175 and 170. So I will just go above for this. We've got a lot of little notes down there. Let's just move this out of the way, maybe. That's notes about this. Can I move? Yeah, okay. I'll do this. Move you down ever so slightly. And you can slide in the top. Right, got some space. What are we saying? We have a man and a woman, and heights between 170 and 175. So we could write down a lot of bits, yeah? These are independent. They're not affecting each other, are they? If I come in and I'm very tall and then someone else walks in and they're very short, it's not because I was tall. That's not why they're short, do you mean? Or vice versa. Doesn't make a difference. Unless they're related, but we don't know that. These are just people playing tennis. So we can just times the two together. We want to work out the probability that we have 170 being less than the height of a woman, and that being less than 175. So a woman being between those heights. And then we'll times it by the same for a man. I'm just going to copy this over, duplicate, change that W for a M, if this will stop moving. Lovely. Where are we going to get this from? I don't know. I do know. That's what I mean when I just show you. We get it from the calculator on the left. What is it, though? It is normals, isn't it? Are we on normal? We are on inverse normal. Let's go to forward normal. Come on, yeah. What was our values again? So for the men, we have 183. Oh no, we'll do the women first on the left. Women, we've just worked those out, haven't we? That's what we've just worked out. So the mean, 171, we'll call that, yeah. The numbers might be slightly different than the actual mark scheme. Slightly different than the rounding, but 171's fine, isn't it? The method's really what you need to learn. 3.877 for that standard deviation. And we wanted between 170 and 175. Calculate. I get, what's that, 0.45. So let's fill that in. 0.4507 times that then by the, what do we call it, one for the men, same range, isn't it? 70 to 175, or 170 to 175. The men, though, a little bit taller, aren't they? Only ever so slightly. 183. Deviation 4.9, bigger range as well. That bit of spread. What's that give us? Oh, very small. That's going to be 0.0473. So let's get our calculators. Times those two numbers together. 0.4507 times by 0.0473. I'm getting a very small number, but this seems kind of normal. 0.0213. So 2% chance. If I go to a tennis club, yeah, tennis, they're giants, aren't they? Tennis players. They are really, aren't they? They're like a whole region of Dutch people, but just like all collated into one club. And we're saying that if we have a man and a woman, then both being, this isn't that tall. This is what, 5'7", 5'8", 5'9", something like that. Man and a woman both being between that height. Woman, yeah. Man, nah. But so both together, nah. Looks good, yeah. Yeah. Last one then. What have we got? Sum, discrete random variable, goes from 2 to 2n. Let's give like this thing. Okay, show that this is a constant. So in this one, it's always the same idea. Add up to 1, yeah? Let's add these all up. What numbers are we going to get? Well, everything's got over k. So I'll just factorize that out straight away. Why not? What's left over is r. That's all these values. Let's just add all those up then. 2 plus a 4 plus a something, 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 plus a 2n equals 1. Got 2's everywhere. Take one of those out. So 2 over k. What we're left with? 1 plus 2 plus blah, 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 plus an n. That still equals 1. I will move this over for the next step. How do we rewrite this? Well, it's n plus 1 over, and then all over 2. Times in that 2 over k. We'll make a k over 2 over there. We can then divide those 2's off. And I think we have the answer, don't we? K is n plus 1. Yep, lovely. Looks good. When n is 20. So what does that tell us about k? Do we need to know? Maybe, but worth writing down in it. It's 420. Find the exact value of r being between 16 and 26, but it can be 16. That you don't have any formulas for this sort of stuff, yeah? You've got no, like, this is just, it's weird, isn't it? Weird, yeah? I think it's weird. You think it's weird. Everyone thinks it's weird. So, you do weird things as well. What numbers are these? 16, 18, 20, 22, and 24. 26 is no. 14 is no to the other end. They're the only ones available to us. And we know, we work out them individually by doing this sort of formula. They're independent. They're not going to affect each other, yeah? We're only picking one, so like they can't affect each other anyway. So what we want to do is add up those numbers and then divide it by k. Because if you think about it, like each one would have over k, over k, over k. So again, it's factorizing it out. Same idea we've been doing up there. Adding all those up, what do we get? Well, the middle one's 20. These are equally spaced, symmetrical distributions, every 2 in it. So it's 5 times 20, 100. So the value should be 100 over k, whatever that is. I will plug in, obviously, the value for k. K was 420, wasn't it? So it's going to be 10 on 42. Well, we'll do it like this, 100 over 420. 10 on 42, 5 on 21. Seems good. It's a number they use quite a lot in these past papers. I haven't got the mark scheme for this. So I don't know if I'm right on these numbers. The method should all be fine, yeah? For the whole thing, method should be fine. Numbers might well be slightly wrong somewhere along the way. So n is still 20. Random variable g of r is taken. Quadratic equation in this. Find the exact probability that the equation has no real roots. Okay, well, how does that work? We need to first of all make this into an actual quadratic where we have 0 on the other side. So we're going to subtract the 3g, no. We're going to leave the 3g alone. And we're going to take away a 5. This then, whole in the end, that is like our plus c. So when we have no real roots, that tells us our discriminant is 0. So, no, not 0, sorry, less than 0. Because when we look at the quadratic formula, we end up square rooting that thing, but we can't square root negatives. Not allowed to keep real roots. So what do we want to find? The discriminant itself is going to be b squared, which is just g, so g squared, plus or minus, no, that's a bit outside it. The discriminant, no, what am I doing? Minus 4 times a. I shouldn't have the x in the middle. That's what's bamboozling me. There we go. Right, that's better, isn't it? Yeah. Yeah? No. What am I doing? Okay. This is a quadratic. Let's rewrite it equal to 0. X squared plus gx plus 3g minus 5 equals 0. I was half a step ahead. Do you mean in my head? This we want to do the discriminant of. This thing's fine. Yeah, discriminant is negative. So what's the discriminant of this? B squared is g, so g squared. Well, b is g, so g squared. Minus 4 times a of 1 times c of all that stuff in the end. Yeah, 3g minus 5. Okay, lovely. So we know g squared minus that stuff. I'll expand the brackets out. I get 12g plus a 20. That needs to be negative. Factorizing it, I get a minus 10 and a minus 2. Yeah, looks good. Yeah, looks good. And just for those that aren't sure on how to do this stuff when it's a quadratic, if we were just to plot this very quickly, doesn't need to be too good. It's a smiley graph, yeah, positive 1, so smiley. So that's going to be a 2. That's going to be a 10. So we're going to be beneath the curve, beneath 0, yeah. So we need to be underneath. So rephrase that, underneath the curve, so beneath these two numbers. So less than the 10, bigger than the 2. This one, we're just looking them up, aren't we? So that's the same as g either being 4, 6, or 8. And here, add those all up, we get 18. So our probability should be 18 over k, which is 18 on 420. So let's do a division on that. 9 on 210, divide them all by 3. Is it 3 on 70? I will double check with the calculator. 18 on 420. 3 on 70. That looks good for me, ladies and gentlemen. Thank you ever so much for watching. Hope you've enjoyed that. I will see you soon.